In this video, I'll be demonstrating the particle tracking tutorial of TransAT. The outcomes of this tutorial are to learn how to set up a Lagrangian particle tracking problem, and also to learn how to use the sub-BC tool to create a sub-boundary condition. Our two-dimensional problem is as follows. We have two velocities in our problem. On the left, we have a u velocity inlet with particles at a volume fraction of 1 e to the negative 3. Halfway through the domain, where we've created our sub-boundary condition, we have a v velocity inlet of particles with a slightly higher volume fraction. In both cases, the particles are inlet with a temperature of 400 Kelvin. We have walls set with a temperature of 300 Kelvin, and on the right side of the domain, we have a pressure outlet condition. The flow is unsteady, and the particles are inlet with the fluid of air. Let's begin the setup of our problem. To begin the problem, I will first set up the domain and grid. I will set the following coordinates for the domain. Next, I will set the number of cells in my domain. In the x direction, I will set 40 cells. In the y direction, 10 cells. And for the 2D problem, 1 cell in the z direction. I do not require any cell ratio, so I will set all of these values to 1. Next, I will divide the domain into 3 blocks in the x direction. And now I can set the boundary conditions. I will define an inlet, an outlet, a wall, and a secondary inlet. For the main inlet, we will set a velocity-based condition of constant u velocity of 0.78 meters per second. In the Lagrangian particle tracking, we'll set a volume fraction of 1 e to the negative 3 and a particle temperature of 400 Kelvin. We do not need to set particle velocity because that is defined by the fluid. Next, I will set a pressure outlet condition. I will confirm for my wall boundary condition that a temperature choice is selected and set to 300 Kelvin. For the particle inlets, I will set a constant velocity condition of 0.87 meters per second in the v direction. For Lagrangian particle tracking, I will set the volume fraction to 2 e to the negative 3 and the particle temperature to 400 Kelvin. Now I will assign the main boundary conditions. To the x-min 0 surface, I will set the main inlet condition. X max 0 will be assigned to the pressure outlet, and the y surfaces will be assigned as walls. Now we need to separate the y min 0 surface into a sub-boundary condition. We would like to add an inlet halfway along the domain. To do so, we'll select the y min 0 surface. Using the Create Sub-Boundary Condition tool, we can use the sliders and define a new section for a boundary condition. Additionally, we can set a coordinate. We'll do so with an x-min of 0.045 and x-max of 0.055. You can see now the new surface that was created. We'll assign our secondary inlet to this surface. This concludes the domain and boundary conditions. We'll save our project. Continuing on, we'll go to the Input tab. For our basic equations, we'll be solving pressure, temperature, u, and v velocity. Under our reference properties, we'll set a reference temperature of 300, reference velocity of 1, and a reference length of 0.1. We can enable Lagrangian particle tracking and set the properties. Pay close attention. For thermal conductivity, we'll set 1, computational ratio of 1, volume fraction 0, number of particle size bins to 5, and for the diameters, a min of 50 e to the negative 6, a max of 200 e to the negative 6, and ensure the size PDF function is set to constant NP. For physics, we'll turn on two-way coupling and leave the SunderM P stencil and enable solve temperature. For forces, we'll deselect buoyancy force. For numericals tab, we'll set the response time factor to 0.1. Under the initialize tab, we'll make sure velocity equilibrium is enabled, and we'll enable temperature equilibrium. For boundary conditions, the particle inflow type will be set to per boundary, and inflow random series will be left as not fixed. For outputs, we'll enable right particle temperature and max particle Reynolds number. This finishes the settings for Lagrangian particle tracking. We'll continue to set our phase properties. Our phase will be air with a density of 1 kilogram per meter cubed, and we'll set a viscosity of 1.7 e to the negative 5 Pascal seconds. The thermal conductivity will be set to 0.026, a thermal expansion constant of 0, and a heat capacity of 1005. Under simulation parameters, we'll be running an unsteady simulation. We can leave the default time of 1000 seconds, but change the time steps to 500. Under advanced options, we'll change the initial time step to 1 e to the negative 3 and leave 20 iterations per time step. We can also leave the auto relaxation factor of 0.6. However, for adaptive time stepping, we'll set the CFL limits between 0.2 and 0.4, diffusion to 0.2 and 0.4, and the Fourier number between 1 and 2. For equations, we'll change all quantities, convergence tolerance increase to 1 e to the negative 3. Continuing on, in initial conditions, we'll set the initial temperature to 300 Kelvin and the remaining variables to 0. Under output management, we'll change the file format to paraview and a frequency of every 20 time steps. We'll ensure the primary variables will be outputs, and we'll select in addition particle volume fraction. We'll also ensure that non-dimensional numbers will be calculated. This finishes the setup. We'll save the project, head to the Execute tab, increase the number of processors, and run our simulation. With the TransAT simulation finished, we'll open up ParaView to view the results. In the results folder, we'll notice that there are two VTM files. One consists of a prefix XY, which contains information for the fluid, and the second VTM file with the suffix particle contains information for the particles. We'll first load the data for the fluid. And we'll display surface information for temperature. We can play the animation and rescale. It will be interesting for our results to see the particles as well. Let's load the results for the particle. And to see the particles, we'll use the glyph tool. We'll choose a glyph type of sphere. We'll choose a scalar of temperature, and we'll change the scale factor. Now we can visualize the full animation, noticing how the particles enter in with the higher temperature and transfer this to the fluid. This concludes the particle tracking tutorial.